Okay, the record is back on. So Napat, could you repeat your question before the break, please?
Is the purlin spacing going to be provided by the manufacturer of the tile?
Generally, it should, yes, because when you look at the catalog of the tiles, they should provide you the information about how it should be installed. So the answer is yes. And generally, it's the architects who handle this kind of thing because they select the materials. So they have the catalog, and they should always have. And when they have, you can simply ask information from them directly. It's okay, we do that, okay? But if you become more familiar with the materials, you will know it right away. And you can also have those catalog for yourself as well, it doesn't hurt. Right. You know, there's one thing that it used to be so popular for the roof tile. It's called CPAC ammonia. It's a very, very heavy material, and it requires some kind of a special framing system for the installation. And in the end, you know, by the dead load itself, it could be something like 50 kilogram per square meter. That one heavy roof tile, a news tile here, it is also heavy. Not as heavy as CPAC ammonia, but I say it's pretty heavy as well. So, you know, there are materials that will be light and efficient, but I'll leave it up to you. Okay. One more thing, the floor here. Generally, there's a floor called the lanolin, something like that. It's lanolin in Thai, it's a kabung yang, perhaps. It's kind of, you know, if you really want your building to look good, you don't want to use that. Imagine you use a lanolin in your bedroom, right? you would not want to sleep there. It depends on the occupancy that you are going to have for your building. It's your choice, okay? So please have fun selecting the tiles and the stuff, okay? And I should say that you should also provide this kind of information. Whenever the information that you acquire from anywhere, you know, you just put it in a nice file so that you have a good reference for yourself in the future. Okay. One more thing, a part of the CLO of this class is for you to be able to find the load and the design criteria and the law and the reference. So when you have all these numbers for the live load, for the day load, do have reference with them, okay? Please also have a reference. That's very important. And your work will be graded on, you know, the reference that you quote as well. And please, there used to be something like this, because you just go on and search for anything available on the internet. So sometimes it happens. I remember some students would use the finishing, the catalog from Bangladesh, for example, because it's there on the internet. So if you, okay, I'm going to use the tie from Bangladesh. So would the owner pay for that? Would it be available in the market? So please be mindful of the information that you have from the internet as well, okay? Any questions? Any more questions? Hello? Okay, I hope that means no. So let's say, is it okay that I start the design example now, folks? Hello?
Yeah.
Okay, so here we are, your first compression member. Okay, Now we are looking at the section H 300 by 300 by 94. Generally, that's pretty big. See the weight, 94 kilogram per meter. So it's a heavy section. H 300 by 300, that's a nominal size. And it doesn't necessarily mean it's the actual size. But this column is braced here on the weak axis. So you see, this is the cross section. It's braced on the weak axis. So when you look at the picture, you see the bracing is right there on the web. It's right there on the web. See? So if you look from another view, you see the bracing as something like this. I can try to draw a 3D picture so that you see it more clearly. Let's say this is our section. Okay. Not easy drawing on the iPad. I didn't really put it down as well. Okay. So in fact, this should be another line like that. The bracing is here. Okay, in that direction. So when it wants to buckle in this axis, about this axis, you see? When it wants to buckle about this axis, it means that the rotation is going to occur like this, right? And it moves to the side like that. So at this point, it can move. So you will see that when you look at this from the y direction, when it is going to buckle, it is going to buckle like this. In other words, the unbraced length in the y direction becomes 4 meters. But in the x, now the bracing becomes just a dot. So when the buckling is going to occur in this direction, rotation like that, this bracing doesn't help, right? So your column can go full blown like that. So the LX becomes 8 meters. Okay, so the properties are given. Now the investigation is really easy, but you have to be able to see how, if you have a system of bracing that differentiates the unbraced length in X and Y direction, you must be able to tell them. So let's say we have 2 failure modes of the compression member. The first one is local buckling, correct? I forgot to mention one thing yesterday, that is, when you look at this section, how to draw it so that you can feel it. Okay, the web is kind of thin always, but the flange is huge, thick. When you consider the slenderness ratio of the flange, is it this distance, B, right? Over the thickness. But for the web, to be fair, you need to consider this distance. It's the distance between the fillet. Okay, this is your B, or they call this H. B, this width B is H. So basically H is equal to the depth minus 2K, right? And K here, oops, sorry. K here is the thickness of the flange plus the radius of your fillet. Remember, this is the fillet. Okay, But also one thing, please note that I actually provide this in my table. You can see we already have this, see, compact section criteria. Every section is provided with this ratio, so it doesn't hurt to use it. Okay, somebody refused to use this and then get it wrong, which is really sad, you know, because all the numbers have been done for you. So you should get it right. If you plan to calculate, notice that, sorry, one more time. This is depth. This is not H. When you want to calculate the slenderness ratio of the web, you must use H, which is equal to D minus 2K. K is here also provided. Okay. Use that, that's fine. So we are okay with that, I suppose. Let's come back here. First thing we should check is the local buckling. So we go with the flange. Okay, the flange, BF over 2TF. So it's B over T this, but this B is BF over 2, right? It's half the width of the flange. So this becomes BF over 2 and then divided by TF. You can use the number from here because the BF is here 300 divided by 2, and then the thickness of the flange is 15 millimeters. So this is 10. And this is H 300 by 300 by 94. If you don't believe me, you can, oops, that's a wrong one. Let's turn this off. Okay. It's going to be a little bit difficult. Okay. 300 by 300 here by 94. So basically it's this one. You see, BF over TF is 10. Okay. We now come back here. So you can either calculate or you can either pick the number from the table. This is 10. So we are comparing this with, because it's the flange, it's the unstiffened element. And so the limit is use this one, 0.56 square root E over Fy. And this is roughly, as I say, 16. So the flange slenderness ratio is less than the limit. But we must check the web as well. Oh, I forgot to say that this is SS400, right? SS400. So Fy here, that's 2500. And then the web. It's H over TW ratio, which if you want to calculate, the H comes from D, which is 300. Minus 2 of the K, right? And K comes from fillet and the flange thickness. So that's 15 plus 18. Then divided by the thickness of the web, which is 10. This turns out to be 23.4. Again, if you come and look at the steel table, you see that is 23.4, right? Now it looks like eyeglasses here. Okay. So come back to design example. So you can pick this up from the table. Some do because they understand what they're doing and they are paying attention in class. Some don't. It's fine because it should be much better if you know how to do it both ways, in case you may have to work with the steel structure that, the hot roll steel sections that are not fabricated according to TIS. You go work somewhere, some other countries, and they don't have this kind of information. You should be able to do it yourself. Okay? And this will be compared with 1.49 square root E over Fy, because this is a different element. And like I said yesterday, this is roughly 42.6. So here again is less. So the flange slenderness ratio is smaller than the limiting value, and the web is the same. So we can call this section compact section. Okay, because both flanges and web slenderness ratio are less than the limiting value. So say, okay, therefore it's a compact section. So we get the big okay. So what does it mean? When you check the local buckling and it's all good, it means that neither the flange nor the web will buckle before your member loses stability. Okay? Is my handwriting okay? You guys can read it? I just look at the screen and it's at some place that look really nice. So is there any question? Let's move on to the second failure. That is the lateral buckling of the entire member. Now it's for the entire member. So you may say this is global or flexural buckling as well. So now you see we have the situation where you have, different unbraced lengths on both locations. So you need to figure this out, okay? And because we have a hinge at the support, and this is also a hinge, so K is 1. And we check both axes. KL over R in X direction. Remember, in X direction, we don't have the bracing, right? So K is 1. The unbraced length, not the length of the column, the unbraced length is 8 meters. But R is in centimeters, so I'm just going to change the unit by multiplying this by 100. Okay, now this is a ratio. It's a very simple thing, and yet some people will make mistakes by not changing the unit. Divided by Rx. Rx is given here as 13.1. Again, this information is right there in the table axis, right? So here is Rx 13.1 and Ry is 7.51 here. Okay. Come back here. So K over Rx turns out to be 61.1. Now K over Ry. Again, K is 1, but why? Because we have bracing this time. So it becomes 4 meters, the unbraced length. Correct? Let's look at the picture again. See, 4 and 4. So they are equal. They are braced. The column is braced in the middle. So we have the equal unbraced length in Y direction. So this has to be multiplied by 100 to change the unit again. And divided by Ry, which is 7.51. This turns out to be 53.3. So what do you say? What does it mean? So we can say this one governs, right? So in fact, because of the presence of the bracing in Y-axis, this guy is going to buckle in X direction before. Why? Because now KL over R in X direction is slender than KL over R in Y direction. So now what do? We now know that this the slenderness ratio of 61.1 governs our design. It's a maximum value, so it's gonna buckle there first. Now we need to compare this slenderness ratio with the limiting value to determine whether or not this column will be in the elastic or inelastic region. So we compare with 4.71 square root E over Fy. This limiting value is, after the calculation, this is 135, which is greater than 61.1. So what do we have here, folks? Nobody wants to talk to me at all. What do we have?
No buckling?
No.
Elastic.
Yes, it's inelastic buckling. It will buckle. Okay. I appreciate you your participation. So that means you're not quite getting a hang of it yet. Your column will buckle. Okay, your entire column will buckle. The question is how. So we determine this. We know that it is going to buckle inelastically. Okay, I can go back and show you this. Quite far away. Here. We design or we predict the strength of the column based on this curve. This curve. Your column will buckle because when it reaches that load, it is going to buckle. So the question is, what is that load? So in order to know the load that will cause your column to buckle, we need to determine first what kind of buckling is going to occur with this column. So we determine this ratio, right? And now we know our KL over R is less than this. So we know that the buckling is going to be inelastic buckling. And the load that will cause this buckling should be predicted by this formula. Okay, does that help?
Yes. Okay.
Okay, maybe it's maybe coming too quick for you. You're not familiar with any of this at all. This is the first time in your life, so it's okay. So your participation will get you into the groove quicker. Okay, so here we are. This is our, what's the beautiful word for it? Design model. Okay. You have this design model, so we are going to design our compression member based on the prediction offered by this set of formulas. Okay, so now we check this slenderness ratio. We know that 61.1 is less than this value, so we are in this region. See, points to the left. It's inelastic buckling, and your strength will be predicted by this formula. Okay. So we come back here. Here. So now we know it's inelastic buckling. So we are going to calculate Fe, right? Yeah, it's still space left. Fe, that is pi square E over 61.1. Square. Don't forget the square. Now look at this. 5390 kilogram per square centimeter. Say, wow, this is bigger than Fy. Is it correct? Yeah, it's correct because this is the elastic buckling load, you know. It's not the critical buckling stress itself. Sorry, this is critical elastic buckling stress. Okay, it's not the critical buckling stress itself. So from this, you can now predict the F critical by using the proper formula, which is 0.658, and power is, you want to write properly, Fy over Fe, and then multiply by Fy. Notice this, ladies and gentlemen. You see, your Fe is the denominator, correct? And this is the power of the number that is less than 1. So if you are going to power the number that is less than 1, if the power is greater than 1, this will keep getting smaller. Am I correct?
Yes.
Yeah, for example, for those who do not see it, 0.5 square, that's 0.25. Smaller. Because 0.5 is a half, right? You multiply a half by a half, so it keeps getting smaller. And this is the same nature. So, in fact, when your Fy is great, when your Fe is greater than Fy, the power here becomes less than 1. And when the power is less than 1 and your base number is less than 1, actually it is becoming larger, you know. So, 1 second. Okay, so let us get going into the calculation. Okay, here is 0.658. The power becomes 2500 over 5390, and then multiply again by 2500. And this comes out to be 2060 kilogram per square centimeter. See, it will never get to Fy. So you should fill your calculation a little bit that the number comes out sensible or not. So from here, I can say that my P nominal is going to be equal to this, multiplied by the area, which is 120. That's right, 120. That's large. So I better change this into tons. As I mentioned before, that this is quite a huge column. So the nominal strength, the calculated strength, gives you 247 tons. Okay, and that means in the end, if it's ASD, P nominal over factor of safety is 148 tons. And if it's LRFD, it's phi PN, that's gonna be 222 tons. So that is it. Very, very simple. Okay. Is there any question? Hello? Any question? Quiet. Is it crystal clear? Quiet still, so I suppose. Now, let's take a look at the next one. Now it's a real design problem. Now let's just see it here. Okay? Select the lightest H-shape SS400. SS400, that's your criteria. It's H. to carry a dead load of 40 tons and live load of 120 tons. So let's just say we're going to use ASD, okay? I have this somewhere. Okay, right. So now, remember that your P nominal is F critical multiplied by AG, right? You don't have the section, so you don't know the area. You don't know the F critical because F critical is a function of KL over R and the Fy. Correct? So what do? We're just gonna have to make a while. Yes, right? But then what we can do is now very simple because of the design table. So you can say you have the load. And your design equation is such that your PA must not be greater than your nominal strength divided by factor of safety. Right? Are you still with me? And this is always your universal question. So that means if we are going to try to determine our nominal strength, I can simply say my nominal strength must be greater than or equal to factor of safety multiplied by the load. Are you with me?
Yes.
You must understand that if you use ASD, the factor of safety, because it's a safety, it should increase the load. So that means we have here that we know the load combination. So the target, your P nominal will be equal to the factor of safety, which is 5/3, multiplied by the dead load plus live load here, right? The total load is 160, but because we move the factor of safety to this side, it becomes 267 tons. So that becomes the target load. Now, this is the table that I give you. I posted yesterday, table 1 and table 2. This is from table 1. Okay, you see that now we have this. We know the unbraced length. So you go to the table with KL equal to 350 because K is equal to 1. You also have to account for K. Okay. When K is equal to 1, this 350, you go to this table. Can you open the table yourselves and you know, work with me so that you know, or you can just look here. Okay. Now that is your unbraced length. KL, because KL over Rx and Y, they are equal. So we come here at the table with KL equal to 350. So now this table will provide you with both KL over Rx and KL over Ry of each member here. And then you have the load for SM, still SM or SS 400 and SM 520, depending on which one you are going to use. This will be the strength based on KL over Rx. And like in other words, no, in the other hand, that's more like, in the other hand, this will be the strength based on KL over Ry. For example, if you look at KL equal to this, for H 100 by 100, it's going to have different K/R for X and Y axis, right? And if KL is fixed, KL/RY should be larger than KL/RX, and therefore it should have a smaller load. You see? And now that means we know because the unbraced length are the same, so we should know now that the KL/RY should govern. And because we use this SS400 by inspection, and say by inspection, the KL/RY, because y-axis is smaller, governs your design. So you come here on this side, and with SS400, so you look at this table. Okay. Now, because we changed this target to nominal, so you now keep looking until you hit the number that is greater than 267. So we are here, 268. You see that? Because we know that the y-axis is going to govern, and we know the material that we are going to use, and we know the target because we move the factor of safety to the load side. So now we know it's 268. Okay, so now we can start by selecting this section and see what happens. Okay, are you with me? Hello.
Yes, yes.
Okay, simple enough. With this design table, your life is very easy. And this is the real work, because I now have this table. So if I have to handle something, I'll do it this way too. So now I select this section. Okay, so out of this, I can now start my investigation, whether or not this section would work. Okay, this is what you should always do. Oops. I have one page left, so let's get on to the new page. So it's, okay, I should say here, try. H 300 by 300 by 94 kilogram per square. Oops, so I'm sorry. All right, per meter. Okay, and now you have the section. You should go to the steel table again and pick the property, but somehow it happens to be the same thing. Okay, but you know the load and the unbraced length are different. So that's the section that we are going to try to see if it works. Okay, so from this, you can take your properties, but since it's the same, so let me just go ahead and investigate it. Okay, so check. First, local buckling. Okay, so you have again BF flange. It's BF over 2 TF. And because it's the same, so let me go ahead and write it down. It's 10, which is less than 0.56 square root E over Fy. So that's 16. And for the web, that's a colon, that's an equal sign. The H over TW, same number, 23.4. Again, you know now that it's less than 1.49 square root E over Fy, which is 42.6. So we'll say now compact section. Okay. All right. Step number 2 is the lateral buckling. So again, we now should check both K over R, even though we know. So your KL over R in X direction, that's 350, right? With the load, with the unit change already, divided by 13.1, and KL over RX. I'm sorry, KL over Y now, 350 divided by 7.51. Or you can just say here that by inspection, KL over RY governs because, you know, unbraced length on both axes are the same. Okay, so this is 46.6. You can also say by inspection. KL over RY governs. Okay, so we got 46.6. So again, we compare this to 4.71 square root E over Fy, which is equal to how much? 135 something, right? Am I right?
135.
Okay, thank you. So now we know it's much more than 46.6. So you have inelastic buckling. Okay, so now Fe is pi square E over 46.6 square. That turns out to be 9,090 kilogram per square centimeter. And oh, I'm sorry, it's just something with a number. Pardon me. It's 9,270. Okay, and the F critical is therefore 0.658, the power of Fy over Fe here, and then multiply by Fy again, the entire chunk. This turns out to be 2230 kilogram per square centimeter. So you see, the slenderness ratio is 46, which is quite low. So you have critical buckling stress pretty close to Fy. And the nominal strength here is 120, that's the area, multiplied by this, divided by 1,000. So 268, you know, just rounding off a little bit with my table. So now you know P nominal here. In the end, you should also make the summary somewhere to write nicely. So therefore, P nominal divided by factor of safety is greater than 160, right? That's all. Yeah. I don't have the number, but it should be somewhat larger. So, okay. In the end, you say we are going to use this. Use H 300 by 300 by 94 kilogram per meter. Okay. So, any question? Any question?
Excuse me.
Yeah.
This one is the verifications of the number in the table, right?
Yes.
So that's mean when we use in the real world, we can use the number that's shown in the table already.
Supposedly, yes.
Okay.
If you believe that all I have done is correct.
Okay. Okay.
Right? It should be correct. But, you know, I think it is always a nice thing to do because, as I say, design is the action where you create something out of nothing. So you will always begin by, you know, selecting the section here. You select the section, and it's not a bad thing to try to verify it, because one thing that you know here, even though the number is correct, but you don't know about the local buckling. Okay, so this process must always be carried out just to make sure that your design is okay. And then you come here. The fact that we can get the final load equal to the number from the table is because we also don't have the local buckling issue here in the calculation. All right. And is there any more question?
Why we use larger KL over R?
Because
Why you-
larger KL over R would mean that it is going to buckle in that direction first. Because you can see it now that this number here is going to be smaller, right? This number is going to be greater. So that means now your y-axis is more slender. So it will buckle here, right? It will not buckle here. And if you don't feel it, one way to help you feel the structure is that you go ahead and calculate this as well. It doesn't hurt. You can go ahead and calculate KL over Rx and then use that number to create F critical. And then in the end, you will arrive here with P nominal. And the smaller KL over R will give you greater P nominal. So now you know which load you are going to choose, right?
Yes.
But naturally, you should feel that, okay, this way is more slender, so it should lose stability in that axis or in that direction first. It's only natural. So but I am okay if you don't feel this. You carry out the calculation a few times and then you feel it, and then you become more confident that, okay, actually the greater number in the slenderness ratio would mean that you're going to get the smaller load carrying capacity in that direction. So that becomes your answer anyway. You can do that a few times, and once you feel it, okay, now you're confident that why you're doing this. I don't want you to memorize it. It's gonna hurt you in the end, because sometimes the memory can play tricks on you. But if your memory is about understanding, you understand the behavior, you've done it, you've seen it for yourself, it's just gonna stick. And you will be extremely highly unlikely to be wrong. Okay?
Okay, have.
Good. More questions, perhaps? All right, guys. Let me stop the record first.